Hello everyone, welcome to my Your Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is replace words. So the problem statement goes like this. In English, we have a concept called root, which can be followed by some other word to form longer word. Let's call this word as derivative. Okay. For example, if the root word is help and it is followed by the word full, then the derivative will be helpful. Okay, so you will be given a dictionary consisting of many roots. Okay, for example, this is the dictionary that is given to you in the example one, and you will be given a sentence consisting of words separated by spaces. For example, this sentence. Okay, so replace all the derivatives in the sentence with root forming it. Okay, so for example, kettle can be broken down into cat plus tle. Okay, so instead of kettle we just put cat, which is the root of this word. Okay, if a derivative can be replaced by more than one root, you have to replace it with the root that has the shortest length. Okay, so you have to return the sentence after this replacement of derivatives with their shortest roots. Okay, so let's have a quick look at the constraints before thinking of an approach. So the length of the dictionary will be of order 1000 and each of its words will be of order 100. It is mentioned that each of the words in the dictionary is lowercase English letters only, and the sentence length will be order of 10 raised to power 6, and also all the words in the sentence will be either spaces or lowercase English letters. Okay, and the number of words in the sentence will be ranging from order 1 to 1000, and length of each word will be of order 1000. Okay, every two consecutive words in the sentence will be separated by exactly one space. Okay, and there will be no leading or trailing spaces in the sentence. Okay, so these are the constraints. So for these type of questions or problems, you can say uh, there is a data structure which is very useful, which is called Trie. For those of you who are not familiar with it, I will try to find an article on this data structure and its link will be provided you on the in the description, giving you the basic implementation of Trie and how and when to use it. So you should definitely head over to the description section of the video and explore that link if you are not familiar with the Trie data structure. The prerequisite to solve this problem is the knowledge of Trie data structure. I will also try to explain it in my own words, but it will be better if you explore that article whose link is given in the description. So without further delay, let's move to the approach. So in a Trie data structure, since we were mentioned that only lowercase English letters will be there, so all the lowercase English letters can be represented by indices from 0 to 25. So what we will be doing is, in a Trie data structure, just like a tree, we will be having some nodes. Okay, each node is having two properties. Uh, Whether this node is the last word of the any last word of any word or not, and its children's. Okay, so its children will be represented by, its children will be obviously tries. So there will be an array of type trie, and we will call this array as children's of the current node, and all the indices will be from 0 to 25 because of the size of the, or the number of lowercase English letters. Okay, so let's take an example. Let's say we are to insert apple into the trie. So what we will be doing is, first of all, we will be seeing what is the first word in the word to be inserted. It is a. Now let's consider that it is in small case or lower case. So what you will be doing is, you will take relative difference of the first word with small a. Okay, and it comes out to be 0. So the 0th index will be chosen as the current node for this character. Okay, so you will be initializing empty trie node, okay, which will be called root. All the insertions and the searches in the trie will be beginning from this root and going down as we proceed further. So the 0th index will be having a. Okay, then this node will be having uh, two properties further, which is end. Is this the end of the word, or, and the second property is its children of itself. Okay, from 0 to 25, which are also of type trie. Okay, these are nodes in themselves, trie nodes. Okay, or you can say trie. So we will move to the next word, which is p. So we will take relative difference of p with a. Whatever this thing comes out, we will insert into the array. So let's say p is inserted here. Then again, two properties, isn't and the children's array, and this way this whole thing will keep continuing. And as when you will be reaching the very last word, which is e, by the way, once you have inserted e, this is end property will be set to true. Okay, so this is end property will help us to determine whether we have formed a word or not. Okay, and the similar, this was for insertion. Similar kind of logic will be applied when we want to search apple in the root. So first of all, you will be searching for the 0th index. Okay, you know that, okay, we are having something at 0th index. Then you will be searching for this p minus a. Okay, then you will find that, okay, we are having something at this this particular node also. Then you will be again searching for p minus a. Okay, then you will again find out that we are having something here also. Whenever this is and condition is true, you will know that, okay, a word is formed here. And if a word is formed and it is the last word, then we will know for sure that apple is in the trie. So this is in what I can explain you in nutshell how trie functions. And I will highly suggest you, if you are still not clear with it, it is better for you to head over to the link in the description of the article regarding trie, and have a complete understanding of it, and then only proceed with the rest of the video. So now we will be, what we will be doing is, I will take the code that we have used to implement the whole logic to the board and try to explain you how things are working out here. It will save some time, and it will make you know, understanding quite easy for you. Okay, so without further delay, let's take the code to the board. It should not be that long, I think. Should It can be fitted well in the boundaries of the board. Okay, it's a little bit long. Anyways, we can scroll it definitely. So let's begin with it. So this is the basic implementation of try. Okay, you are just inserting values in the try. Till here it is the basic implementation. And first, as I told you, we will create a class representing a try node. Each node will be having two properties, children and isEnd. IsEnd will be initially set to false, and there will be 26 try nodes in the form of childrens of every node. Okay, and as I told you, for the insert function, what we will be doing is, first of all, we will be starting from the root. Okay, so the root will be a empty try node that you will be initializing, and then you will be using it to store or search the values into the try data structure. Okay, so let me get rid of this toolbar, and then what you will be doing is, you will be visiting each character of the given key or the word that is to be inserted into the try one by one. Okay, and what will be the index at which the particular character will be inserted into the try children's. It will be relative difference of that character with small a, because all the characters are lowercase letters. So if the index at which this current character is to be inserted in the children's array of the current root is null, it means that we have to create a node there. Okay, initially all the values will be null, so then we will create a new try node there. Okay, and now the created try node will be having similar structure, all the children's value set to null. Okay, and isEnd set to false. So this created new try node will be having similar structure. Then you will now, root is kind of a pointer. Okay, which is pointing to the current node at which insertion is to be done. Okay, so then you will shift your root just like here. Firstly your root was this a. Let me change color here. Yeah, this should be fine. Firstly your root was this. Okay, let's say this was the root at which you started. Then you inserted its a into one of its children. Then your root value became this. Then your root value became this one. Then your root value become this one. Then this one, and at last e. Okay, so this is how things are approaching here. Okay, now moving back towards the implementation code. So you will keep updating your root. Okay, once you have updated your root, then you will mark that when you will be at the last word. Okay, let's say apple was to be inserted, and when you are at e, the root representing it, you will mark that okay, this root represents the end of a word, which is represented by marking is end you know property of this try node as true. Okay, so similar kind of logic will be there in find. Okay, just like this, I will explain you the find logic in a little bit. For before that, what we will be doing is, we will try to understand how this trie data structure will help us to find the roots of possible roots of each word in the sentence. Okay, first of all, what you will be doing is you will take the entire dictionary, and for efficient searching of the roots of each word, we will add all the words in the dictionary into a trie data structure. Okay, so a trie like data structure will be having all the words of the dictionary. Then for the words of the sentence, you know one by one for each word, we will try to find out a possible smallest possible root for that word. Okay, so first of all, you will be declaring a root for try node, which I told you that empty root will be initialized. Then you will be adding all the words of the dictionary into the try data structure. Okay, so this is for efficient searching of roots of each word in the sentence. Okay, so first of all, as it was mentioned in the problem statement that there will be no trailing or leading spaces in the sentence, only the words in the sentence will be separated by empty spaces. So we will split the sentence with this empty space. Okay, and it will give an array of words which will be the words of the sentence. Okay, then we will traverse through this words array or the words of the sentence one by one and try to find out their smallest possible roots. Okay, so now we will try to understand what is going inside the find function of the trie data structure. Okay, although it's quite similar to the insert function, all the logic is very much similar, but there are little tweaks here and there that we have to understand. Okay, so this string builder is of no use, you can very well remove it. Okay, first of all, you will be starting from the root. Okay, which is this node that we have initialized here. Then you will find out the insertion index, at which if there is a you know insertion index corresponding to the current character of the key. Okay, so although the words of the sentence are not inserted into the dictionary try, you can call this dictionary try. So we will be finding out the matches uh, which will be there from for the roots and the current word. Okay, so if there is a no match for the current character, then we will know that okay, there is no possible root for the current word. In that case, you will break this entire loop and you will just return the current word, saying that there was no root that was present in the dictionary for the current word. Okay, but if it is not the case, then we will proceed further. Then we will, as there as we have done in the insert statement, update the current root, which is the thing that we are doing here. For example, first of all the root was this, then it was updated to this, then it would the root is again updated to p, then again updated to the second p, then again updated to the l, then again updated to the e. So this is what we are doing here, and this is just a relative difference of the current character with a, which will be the insertion index. Okay, so we will keep doing this. You can very well delete this line also, so it is of no use. No, no, no. Pardon, please. This results string builder will be of use, and it is of use also, because as soon as we hit, we know that okay, there is some word ending here. It means that some uh, root in the dictionary is ending while we are searching for the current word into the dictionary. Okay, it is something like this. Try to understand it. Let's say we are searching for apple. Okay, and a is a word in the dictionary, root in the dictionary. Okay, then as soon as you will be searching for the very first character, you will arrive at this point, and at this particular point, this a will be having is and as true. Okay, so in the result string builder, you will be forming the matches that are the characters that have been matched till now. For example, a, it will be having as of now a in it, and as soon as we found out that okay, this is some end, then we will know that this is the smallest root possible for the current word into the which is in the dictionary. Okay, so you will be returning this result string builder as your answer. Okay, so that's why it will be of use. Okay, so if we have found out that uh, this is the root, there is some root ending here, then we will return the number of characters that have matched already. For example, let's say at this point we found out that till here app is the root, then this result string builder will be having a p p as its current state, then we will be returning it as it is. Okay, else if all of the things are matching, it is entirely possible that this entire string is possible present itself as the root, then you will return this string itself. Okay, so this is how everything will work out, and this is the whole implementation. Okay, and for the for every character you will be finding the possible root, and then you will be reconstructing the sentence by adding space between every two words, and at last you will be returning the reconstructed sentence. Okay, so this is how we will be solving it. And as far as time and space complexities are being concerned, so time complexity wise, you can say that it will be size of the dictionary. Let me change color here. So the size of the dictionary into maximum size of word. Why maximum size of word? Because each character in the insert statement, in the insert function, is visited one by one. Okay, so that's why size of the dictionary into maximum word size of dictionary. Okay, and plus the size of the number of words in the sentence into how many times this loop will run. This for loop I am talking about. Okay, this will run only at maximum word size of dictionary. Okay, because at a certain point, if let's say you are not matching with the current word, then this loop will break. So you can say that it will be maximum number of words in the sentence into maximum word size of dictionary. Okay, so this will be the time complexity, and space complexity wise it will be the size of the dictionary into maximum word size of the dictionary. Although it can be less than that, but we can take a loose upper bound and say that it will be size of dictionary into max word size of dictionary. It is a loose upper bound. It will be, or it can be less than that, but this is a loose upper bound. Okay, maximum word size of dictionary. And let's see what are these sizes in the constraints. So the dictionary length is of 10 raised to power 3, order 10 raised to power 3. Maximum word size was of 10 raised to power 2, and number of words in the sentence was 10 raised to power 3, and so number of words was 10 raised to power 3. Okay, this one. And again the maximum word size was 10 raised to power 2. So this whole thing will be 2 into 10 raised to power 5, order of 2 into 10 raised to power 5. So it's quite manageable. There is a limit for the number of operations, which is 10 raised to power 8 operations limit. So these number of operations are very well within the limit. So we will not be getting a TLE, and the solution will be getting accepted. As per the space complexity, the dictionary size was 10 raised to power 3, and word size, maximum word size will be 10 raised to power 2. So although it's a loose upper bound, but you can say that it will be around order of 10 raised to power 5. Okay, which is generally this much size you can take. Okay, and so these will be the complexities. And if you are still having any doubts in the implementation or any kind of doubts, then you may ask them in the comment section or any queries. And I hope this solution walkthrough added some value to your journey of owning your DSA skills. And I will see you in the next video. Till then, keep practicing and keep solving problems. Thank you for watching.